Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Paul Davies, who's come to us from Arizona State University, where he's the director of the Beyond Center. Paul did a bachelor's in physics at the University College London, and also his PhD in the quantum theory of Wheeler and Feynman and electrodynamics. And then he did a postdoc at Cambridge with Fred Hoyle. And Paul has since then carved a impressive career in science and science communication. He has several awards that I'll just take a couple of as examples here that he's been presented in his career, including the Faraday Prize from the Royal Society for Science Communication in 2002, the Kelvin Medal of the Institute of Physics in the UK, and the Templeton Prize in 1995. And in 2007, he was made a member of the Order of Australia by the Queen of Great Britain, of course. So, Paul, as I mentioned, has recently moved from Australia, where he was a long-time resident in South Australia and then Macquarie University. He's moved across to the Arizona State University, where he continues his research and has now opened an interest in oncology research as well. But today he's going to talk to us about a long-standing interest of his, which is time travel and how to build a time machine. So if you'll join me in welcoming Paul.
Well, thank you, Adrian, for those kind words of introduction and the remarks about the Queen. Ladies and gentlemen, Star Trek fans long have claimed that space is the final frontier, but they're wrong. Time is the final frontier. 100 years ago, space travel and time travel were just so much science fiction. Today, space travel is commonplace. So could it be that in another 100 years, time travel will also be commonplace? Now, the great thing about time travel is it's very easy to imagine. You step into some machine or some sort of box, you press a few buttons, and you step out again, not just somewhere else, but somewhen else. Very easy to imagine. But can it really be done? Well, I hope by the end of the lecture this evening, I shall have convinced you that the answer to that question is a resounding maybe. The subject of time travel really took off with the trailblazing novel written in 1895 by the science fiction writer H.G. Wells, The Time Machine. And that sort of set the gold standard for what time travel would be like and what time machines would be like. We could almost think of this as the archetypal time machine, as this cartoon makes very clear. But it does have a sort of Victorian contraption air to it. And so these days, the basic story of time travel has been copied again and again and again, but these days in rather more of a technological guise. And I suppose any particular year, there's another time travel story or another time travel movie. Lots and lots of them coming out. But that's fiction. If time travel could be done, what would a time machine really be like? Would it be like H.G. Wells? This is the remake, incidentally, by the great-grandson of H.G., Simon Wells, the remake of the Hollywood movie in 2002, still with that sort of Victorian feeling to it. So would it be something made of brass and lenses and light and levers and maybe steam coming out? Or would it be more like the DeLorean car of Back to the Future? Or better still, would it be like the famous police box in the Doctor Who series? Now, when I'm talking about this in the United States, I usually have to explain what is a police box, because I don't think they ever existed here. And in fact, very few of them existed in Britain. But when I was a lad growing up in London, you'd see these things. Now, the traditional British telephone box looks like that. It's a red box, you see, but the police wear blue uniform and they wanted a blue box for themselves. And so they used to go in to make telephone calls. That was before the days when the British police forces could afford two-way radios or cell phones, I guess they use now. So that was their means of communicating. And then, of course, technology overtook it, and these police boxes rather disappeared. So I wrote a book on time travel in, I think it was 2002. And one of the London newspapers said, well, we must do some publicity for this book launch. Let's go and find a Doctor Who-style police box. And we scoured the whole of London. And for those who are interested, just outside Earl's Court Underground Station, there remains a police box. There it is in the bottom left. It's still there. So we did a photo shoot, and that you could imagine that the vehicles passing by were sort of slowing down, seeing me standing there being photographed. Obviously thought I was being auditioned for the next part of Doctor Who, but sadly not. It was just the book launch. But all of these are ways of imagining how we might use some sort of technological gadget to transport us through time. So the idea is easy to visualize, but the question is, where is the science fact underlying this? Well, it was only 10 years after H.G. published his trailblazing novel that Albert Einstein came along with his special theory of relativity, published in 1905. And that theory is fundamentally a theory about the nature of time, or space and time. But the centerpiece of the theory, as far as our story is concerned, is Einstein's claim that time is in some sense elastic. What does that mean? It means that time can be stretched or shrunk depending on your frame of reference. It means, briefly, that your time and my time can get out of step. Very simply, we merely need to move differently. And I'll just demonstrate this here. I just need to walk up and down. My time, that is that in my frame of reference, the duration between two events, like me turning around at each end, is different from the duration that you judge it to be. The only thing is this difference is so minuscule that nobody's going to notice. Now, if I were to get on a plane and fly to London and come back again, if I take an accurate clock with me, and I'm talking about clocks which are really off-the-shelf technology, not anything super-duper fancy, then when we compare our clocks at the end of the journey, they will be discrepant by a few billionths of a second. So hardly a Doctor Who-style adventure, a few billionths of a second, but nevertheless easily measurable with modern technology. So there's no doubt about this prediction that Einstein made in 1905, that time is affected by motion. There's no doubt about it. It's simply a fact. It's a done deal. We've done it. But to see what that actually means in terms of time travel, let me just illustrate this by a parable. So first of all, here is me jetting off. Well, you can't do it by Concorde anymore. Jetting off to London, and in effect, the time runs slower in the airplane. But a better way of envisaging this, a very well-known way, is the so-called twins effect. Imagine a pair of twins, let's call them Sally and Sam. And Sally, the adventurous twin, decides she'll go off in a rocket ship at close to the speed of light, because in relativity, the speed of light is what determines the scale of effects. So if you can get close to the speed of light, the time warping or time stretching effects become dramatic. So Sally goes off at close to the speed of light to some nearby star, turns around again and zooms back to Earth. And Sally looks on her watch. How long did the journey take? The answer is 2 years, say. But when she gets back, she notices that in the 2 years in the rocket, 20 years have elapsed on Earth. So Sam, her twin brother, lazy boy, stays at home, is now no longer the same age as Sally. So So Sally and Sam were born on the same day, but they're now no longer the same age because the duration of time in their separate frames of reference has got out of step by 18 years. In effect, Sally has leapt 18 years into Sam's future. And again, this is a real effect. So this isn't just something hypothetical or something from science fiction. It really happens. Now, to make it happen by 18 years is not a matter of principle. It's not a matter of fundamental physics. We know the physics is correct. It's just a matter of money and engineering, that you need to move sufficiently fast for sufficiently long. If you can get, the closer you can get to the speed of light, the more you can leap ahead in time. As I've indicated, at the moment, it can be done by billionths of a second with no problem at all. But to do it by years, that's beyond our current technology. But the principle has been established. So in principle, if you said, well, I'd really like to visit the year 3000, not a problem. Just find a very rich philanthropist. And you might think, well, I'd like to go to the year 3000. Maybe they finally have invented a proper can opener. Or maybe the world is inhabited by beautiful young women who live off the side of cliffs in strange shells. So that, like in the remake of H.G. Wells, maybe all of these things. Well, you could find out. You just need to spend enough money and move fast enough, and you can get to the year 3000 in as short a time as you like, 1 year, 1 month, whatever. So it's an engineering challenge, not a physics one. That's the important point I want to get across. The only problem is that you can't come back again. That is, if we imagine in the Sally and Sam scenario, Sally decides, well, it's all very well visiting Earth 18 years in the future, so to speak, but she'd like to go back again and be the same age as her brother. She turns around and reverses her trajectory. It just takes another 18 years into the future. So it's one way in time only. So getting to the future quicker, which in effect is time travel into the future, is something that is straightforward. Now, I've mentioned that all you need to do is move very fast. There's another way you can do it, and Einstein already figured this out in 1908, and that is to use gravity. Gravity has the effect of slowing time. Time runs a little bit faster up on the roof than it does down in the basement. And again, this is a measurable effect. You might think, well, nobody could ever notice such a thing, but it can be measured, was measured in the 1950s, of all things, was measured the difference between the bottom and the top of a tower, the rate at which clocks tick. There's now no doubt whatever. The most direct test is to put a clock in a rocket and shoot it into space. So time, so to speak, runs a little bit faster in space than it does on Earth. Again, we're talking billionths of a second, but it's an easily measurable effect. Now, when these experiments were done back in the 50s, 60s, and 70s, it was really to test the fundamentals of Einstein's theory. But today, this is a matter not only of practical engineering, but of money-making commercial activity. Because the most important example of time warping at work, making dollars for somebody, is the global positioning system, because that depends on a network of satellites that are both moving in and out of the Earth's gravitational field and moving rather fast, nowhere near the speed of light, of course. And the relativistic effects, the time warping effects of both motion and gravitation have to be factored in. Otherwise, taxi drivers would get lost within half an hour or an hour, or depends exactly where they are. So, in other words, these time warping effects are so well known, they are now a matter of everyday engineering. So there's not the slightest doubt that these effects are real. The question is, can they ever be big enough to give us a Doctor Who type adventure? Well, obviously, I've mentioned if you can get close to the speed of light, you can go into the future a very long way. If you could get a very large gravitational field, you could go a long way into the future. One place where there is a large gravitational field is here. This is the Crab Nebula, very famous. This was the star seen to explode in 1054 by Oriental astronomers. You look at the sky now in that area, and what you see is this ragged cloud of gas. This was a star that blew itself up, and the cloud of gas is the debris from the outer regions of the star, but the core of the star imploded to form a ball of neutrons, a so-called neutron star. Neutron star is an awesome object. It's like a mass of 1.5 suns squashed down to about the size of San Francisco, or the size of maybe the Bay or something like that, and probably spinning, well, up to hundreds of times a second. So this is a fantastic concept. So here, the material is so dense that a teaspoonful, if you went there and scooped up a teaspoonful of this neutron star matter, will weigh more than all the continents weigh here on Earth. So gravity there is intense. And if you put a clock on the surface of the neutron star, it would tick at about 70% of the speed of the clock on the wall. In other words, time would be slowed by about 30% relative to Earth time. So that's a really big effect. But is there any limit to the amount by which gravity can slow time? Well, let me invite you to think about this experiment. Supposing we took the Earth and we keep the total amount of matter, but we squash it to a smaller size. Now, you probably know gravity weakens with distance. So if you squash the Earth to a smaller size, the gravity at its surface goes up. So you'd feel heavier. And then you squash it more, you feel heavier and heavier still. And if you go on squashing it, now the other way you can measure the strength of the gravity is how fast you have to shoot something up in the sky for it to escape, the escape velocity. How fast does it have to go up to escape and never come back? And the more you squash it, the more intense that gravity becomes, the bigger the escape velocity. And so when you squash the Earth down to about this size here, about the size of a pea, the escape velocity from the surface of the Earth would be equal to the speed of light. And then you would conclude that light could not escape. Now, astonishingly, this was known already in the year 1783 by this man here, John Michell, the rector of Thornhill, a clergyman. And he applied Newton's theory of gravitation, this is before Einstein, Newton's theory of gravitation, to work out how big a star should be or how compact a star should be in order that light should not flow out of it. He said quite explicitly that light could not arrive at us. So he predicted the possible existence out there in the universe of black stars, stars that were black because their gravity was so intense it would not let light escape. Now, one way of thinking about this is that if we think about gravity as slowing time, and here we are on Earth, time is slowed, so everything's moving slower and slower and slower relative to us. So it could get to the point where light could not escape because light is in effect trapped. It cannot move or make any progress out towards us because time stands still there. Time is frozen. And for John Michell, this was not his way of thinking of it in terms of time, but after Einstein, that's the way we think about it. And we no longer call these black stars. We call them black holes. Black holes are the ultimate time warp. A black hole, the surface of a black hole is, in a careful sense, you have to be careful, relative to us, a place where time stands still. So it's an infinite time warp. So if you were to go very close to the surface of a black hole and reside there for a year or 2 years or 10 years and then come back out again, you would find that an enormous duration had passed in the outside universe. And if you were unfortunate enough to fall into the black hole, to cross the horizon, then all of infinite future would have passed by in the universe outside. So one of the reasons that a black hole is a one-way journey to nowhere, you can fall into it but you can't get out of it, is because if by the time you've fallen in, everything that can happen in the universe outside has already happened, then you couldn't come out again because to do so you'd have to come out before you fell in. But, you see, that's the key to going back in time. That brings me on to the next part of the talk, because going forward in time, as I've said, is a done deal. We've done it, not in very exciting amounts, but nevertheless, we know in principle that we could travel forward in time for as far as we want it. But going back in time, that's a tougher proposition. So that's what I'm going to come on to now, traveling back in time. And so the wormhole gives us, the black hole rather, gives us a bit of a clue. But there's a history to this, which I'll just take you through, because when Einstein first formulated his general theory of relativity, he was really worried about the possibility of travel back in time, because he knew that would unleash all sorts of paradoxes that I'm going to talk about in a moment. He didn't want it. Basically, he was opposed to the idea, but he couldn't prove, there was nothing in his equations to show that it was impossible. Now, you probably know that in the 1930s he moved to the United States and he had a job at Princeton University. He was very old by then, and not many people used to talk to him. He was a rather isolated figure. Physics had moved on and people were working on particle physics, quantum physics, things like that. And so Einstein used to say that the only reason that he went to work in Princeton was to walk home with Kurt Gödel. Now, Kurt Gödel is an interesting character in his own right. Gödel was an Austrian logician, a mathematician, did some of the most profound work in the foundations of mathematics. But evidently, when he was chatting to Einstein, going home, then they must have talked a bit about space and time and relativity and so on, because Gödel in 1949 produced a solution to Einstein's equations that indicated that you could indeed travel back in time using a gravitational effect. And the effect he had in mind was somewhat unrealistic. It was that if the whole universe is rotating, it would be possible for an astronaut to leave any one point in space and travel not only to any other point in space, but any other point in time as well, including into past time, if the universe is rotating. Well, at that time it didn't seem unreasonable because, after all, the Earth rotates, the Sun rotates, the galaxy rotates. Why can't the whole universe rotate? Today, not many cosmologists believe that because the cosmic background heat radiation left over the afterglow of the Big Bang gives us a wonderful frame of reference that would dramatically, very sensitively show any rotation of the universe, and we can't detect it. Incidentally, Freeman Dyson, who was also at Princeton at this time with Gödel and Einstein, told me recently that when he first went to Princeton, Gödel was one of the few people who would talk to him, and this idea that you could have a time machine by a rotating universe was not just an idle speculation. He was really seriously interested as to whether this was a possibility, and he would phone Dyson from time to time to say, have they found it yet? Have they found it? Meaning, have the astronomers found the rotation of the universe? Anyway, today not many astronomers really believe that, but there are other possibilities for time travel, and the most popular one is the wormhole in space. Now, a wormhole is like a black hole, only different. I've said a black hole is a one-way journey to nowhere. You can fall in, but you can't get out again. A wormhole would be like a black hole in as much as it would be a compact object with an intense gravitational field, but this time you could fall through it and come out somewhere else, and you could look through it and see somewhere else. So there's all sorts of stuff out there on the internet of what it would be like if a wormhole crossed our line of sight. Here's one with a star. Or what happens if you have a spacecraft and plunge into a wormhole. Now, a nice analogy to a wormhole is actually, there's a lot of Hollywood in this, another Hollywood movie, which is Stargate. So a wormhole's a bit like a Stargate, because if we had a wormhole, say where it says exit over there, supposing that's not a door, but that's actually a wormhole, and I leapt through it, I wouldn't come out in Mountain View. I might come out, say, on the other side of the galaxy. So that's the concept of the wormhole. It's a shortcut between two distant points in space. Now, how can that happen? So let me just teach you a little bit of general relativity here on the run. I've mentioned that gravity warps time. That was one of Einstein's central predictions. But it also warps space. And people have difficulty understanding how can space be warped, because space is sort of everywhere. How would you notice? Because we can really only think in two dimensions. But what space being warped would amount to is the following. Imagine drawing a triangle around the sun, a flat triangle. I'm not talking about a warped triangle, a flat triangle. Now, back in the good old days, when students used to actually learn geometry at school, do you remember that, some people? Right? Okay, we used to learn that the three angles of a triangle add up to 180 degrees, two right angles. So that's part of Euclid's geometry. Well, if you draw a triangle around the sun and measure those angles carefully, and people have done this, not literally with drawing a triangle, but they've done it with radar and fancy techniques, then the angles add up to just a little bit more than 180 degrees. And so one way of expressing this is that the sun warps the space in its vicinity, or that the sun's gravitational field manifests itself by warping both time and space. So space can be warped. Sometimes you hear the term that it can be curved. Now, the difficulty about presenting talks about curved space is always that I can't show you a picture of curvature in 3 dimensions. So I can only ever show you 2 dimensions. So just go with that for a moment, and I will show you what a wormhole looks like if we had 2 dimensions to represent 3. And so what you see here is a curved sheet. If I had a sheet, here we are, let me demonstrate this. Supposing this is space, 3-dimensional space represented just by that 2-dimensional sheet. And what you're seeing here is it being curved around like this, such that 2 points come together and touch and with the throat of that wormhole. And so the idea here is that the wormhole connects 2 points which would otherwise be a long way apart to form a shortcut. And so if such a thing could exist, then it would be a means of getting from A to B much faster than the conventional way of going through normal space. And the term wormhole was coined by John Wheeler, the astrophysicist John Archibald Wheeler, in the 1950s for quite a different purpose. He was also the person who coined the term black hole. So they sound the same, black hole, wormhole, but they're very different. And we know black holes exist. They're out there. Astronomers have discovered them. But we don't know at this stage that wormholes exist. But at least we know what they should look like, in care of some of the people who work in this very building, because you'll all have seen Jodie Foster falling through one in the movie Contact, which was not a movie about time travel. It was a movie about space travel and aliens. Seth Shostak tells me that the movie people came here to the SETI Institute to ask, what would it be like going through a wormhole. So when you see the special effects in that movie, you can blame them for the sparks that, it looks like a bit like going through the London Underground. But anyway, the point is not what would it really look like, but can these things actually exist? Now, I've said that if a wormhole exists, it's like a shortcut between 2 points in space. But why is it also a time machine? Well, here's Jodie falling into the wormhole, and she's got to fall through from A to B. And in that configuration, it's just a rapid transit method. It's not a time machine. But to turn it into a time machine, what you have to do is this. You have to take this wormhole and there's one way of doing it, bring a neutron star close to one end of the wormhole, one mouth of the wormhole. Now, I've already told you that neutron stars make time tick more slowly, so to speak. And so if you position it at one end of the wormhole, then there'll be a discrepancy between the clock rates at one end of the wormhole A and the other end B. And then if you after a while, take the neutron star away again, you'll have a permanent time difference between A and B. So if you jump through the wormhole in one direction, you'll go, say, 10 years into the future. And if you jump through in the other direction, you'll go 10 years into the past. And now that raises the exciting possibility that you could jump through from A to B and go, say, 10 years into the past, and then zoom back through ordinary space, where time isn't especially warped, and get back to A before you started out. In other words, you could not only visit the past, but you could visit your own past. You could go back to a time before you went through the wormhole. So physicists call this closed time-like world lines, so I won't get into the terminology. So just a little point of history. The movie Contact was based on Carl Sagan's famous novel of the same name, and it was primarily, as I've mentioned, about SETI and aliens and space travel. But he did want to check out, and he invented the wormhole as a fictional device, but he did want to check out whether it would actually work. And Kip Thorne and his colleagues at Caltech, as a sort of bit of recreational physics, decided they'd look at this, and they soon discovered that the conditions for a wormhole to exist were rather stringent, but not obviously completely unphysical. But that they would soon recognize if wormholes could exist, they could be turned into time machines. So they're more famous now, I think, for time machines than for space travel. Anyway, they're not without their problems, because to traverse a wormhole would be a risky undertaking. And one of the problems about it is what we call spaghettification. anytime there's an intense gravitational field, there is this risk of spaghettification. And let me just try and demonstrate this to you. I don't know if there are any skydivers here. I haven't done it myself. But if you jump out of a plane, then, of course, eventually you reach terminal velocity. But when you're in that period of free fall, you're weightless. And, of course, astronauts would be a better example. But let's imagine you jump out of a plane vertically like this, and you're weightless. But your feet are a little bit closer to the center of the Earth than your head. So gravity is a bit stronger at your feet than it is at your head. And so your feet are pulled a bit more than your head is pulled, so that stretches you lengthways. But each shoulder is trying to fall towards the exact center of the Earth, which is a point. So they're on converging trajectories. So you're squeezed this way and stretched that way. That's why it's called spaghettification. You wouldn't notice the effect jumping out of a plane, but you try jumping through into a black hole or a wormhole, and this effect could be totally huge. There's other horrible things as well. There could be radiation. There could be unknown fields which are responsible for keeping the wormhole stable. All sorts of other things that could be very risky. So the fact that wormholes might in principle exist doesn't mean that this is an immediately practical proposition. But what interests people like me, that is physicists interested in fundamental questions about the nature of reality and the nature of the universe, is can such a thing in principle exist? Now, the wormhole is not the only model on the market. I mentioned the rotating universe. Doesn't seem to be rotating. The wormhole, maybe they're out there. But there are other models as well. This is Ronald Mallett's design. He says if you have light going around and around in a spiral like that, that is one way of creating a time loop. Then there's Richard Gott. He's got cosmic strings, which are threads that may or may not exist in the universe with enormous mass per unit length, moving at close to the speed of light past each other, and the time traveler would do sort of a wiggle in and out these strings as they moved, and that could take you back in time. But my all-time favorite alternative model time machine is John's model. When I decided to write this book on time travel, I thought, well, I'll just check, on the internet, see who's out there, see what people are working on. And I came across John's model. So John is from the year, I think, 2034. And he works for General Electric. So they're into time machines in 2034. And he made the trip back and was kind enough to provide some photographs of the time machine and even to provide the manual for operating it. And I thought, well, this was really good. If I was going to be publishing this book and doing publicity, wouldn't it be great to have John on hand to say, well, it's quite correct. It's really be done. I've come from 2034. So I tried to track him down, but unfortunately he's returned to 2034. So I should just have to wait a couple of decades before I can interview him about it. But there we are. So now I still favor the wormhole as the best way of doing time travel. And so the obvious question is, where do you get your wormhole? Now, one possibility is that nature has been kind, and when the Big Bang went bang, it coughed out wormholes, and that they're just out there, and all we've got to do is find one, harvest it, harness it, turn it into a time machine. Are they out there somewhere? Well, astronomers have half-heartedly searched for wormholes in space, haven't really seen anything. And so we just don't know whether wormholes exist threaded into the nature of space out there on a large scale. But one place where physicists are pretty sure wormholes do exist is not outer space, but inner space. That is, not on a very large scale of size, but on a very, very small scale of size. And I mean small. I'm talking 20 powers of 10 smaller than an atomic nucleus, the so-called Planck scale. And here's a picture to illustrate this. And I'm not going to go too much into this. I just want to say that when quantum physics, which is all about uncertainty and fluctuations, is combined with gravitation, then the prediction is that on this ultra small scale of size, the apparently continuous nature of space and time become disrupted and break up into a sort of foamy or frothy structure. So that if there was some way of reaching down into this space-time foam and grabbing hold of one of these little tubes of space and then inflating it up to everyday Jodie Foster size, and then stabilizing it and doing all the other stuff to it to turn it into a time machine, well, then you'd be in business. Now, how do you go about that? Pressure of time, I'm afraid I can't tell you. But you can read about it in my book. The 4 steps that you need to take to harvest one of these tiny wormholes. Right at the end, I'll tell you about what is possibly an easier way of doing it. But let me just move on to the inevitable paradoxes. So let me take an optimistic view that one way or the other, one day, we will gain control over space-time, we will have wormholes, or that there's some advanced alien community that did all this a long time ago, and the aliens can come and lend us their time machine. Then we're faced with the problem that we can go back in time, and all of the paradoxes that make time travel stories so fascinating would then be unleashed. What are we going to do about that? Well, you remember in Back to the Future, Marty McFly goes back and becomes sort of embroiled with his mother's love life, thus threatening his own existence. Well, let me give you a more brutal version of the same thing. So it's often called the grandfather paradox, but I'm going to call it the mother paradox. So supposing the time traveler goes back in time and shoots mother dead. What then, you see? So it would be a fascinating thing to try, wouldn't it? Yeah. So, you know, if mother is dead, if the time traveler's mother is dead, then the time traveler is never born, so the time traveler can't go back in time, and so we get sort of contradictory nonsense. So that, you know, really brings it home to you that traveling back into the past has paradoxical effects. Now, it's not only going back, say, 50 years and carrying out this murder that gets us into trouble. We could go back just one day, and then we would meet our younger self. What would that be like? That would be pretty weird. There would be 2 of you then. And by extension, you could just go on doing it again and again, and there could be any number of you. So physicists have a great belief in things called conservation laws, and this looks like it would violate lots of conservation laws, but it does have one bright side. This time travel research, as I've said, what you need is lots of dollars if you want to do time travel. Where are the dollars going to come from? You don't have to worry, because you could do this with gold bars and do it enough times, and you'd have enough money to pay for the time machine. Now, the weirdest paradox of all is perhaps less dramatic, but it's one that sends shivers down the spines of most theoretical physicists, because let me tell you the paradox first. Imagine that the time traveler goes ahead, say, 5 years. Imagine it's me. I go ahead 5 years in time, and I get out, say, still in Phoenix. What am I going to do? This is amazing. I've gone 5 years in the future. Probably soon get quite bored. But the one thing I would do is go to the university library and check out the journals. Look at some mathematics journals. What's new? And supposing I then note down a wonderful new theorem that has just been published. And I think, well, that's pretty neat. And then I decide to go back in 5 years. So I've gone forward in time, but I can go back in time, because we're talking about backward in time now. Go back, and I go to one of my students, and I say, look, this is a really neat theorem. Come up with a proof for this. And the student does, and the student then publishes it in a mathematics journal, and that's the very journal that I have read. And so that raises this profound question. I'll leave the proof as an exercise for afterwards. But it raises that profound issue about where has the information of this theorem come from? It didn't come from the professor or the time traveler, because he just read it in the university library, but it didn't come from the student, because the student learnt it from the professor. So here is knowledge, not just information, but knowledge that's come into existence in the universe from nowhere. And so that seems deeply anti-rational. So scientists who believe we live in a universe that's rationally ordered then gets very upset by the prospect that we could have these sorts of causal loops that would introduce into nature this type of informational chaos. And for that reason, a lot of famous scientists say time travel is impossible. Here's one, though Stephen keeps changing his mind. He likes to do U-turns, and I think he's changed his mind on this one a couple of times. I'm not sure where he's at the moment. But by and large, these paradoxes, I think, make a lot of physicists agree that that there's nothing in known physics to forbid travel back in time, but if we permit it, then we run into very serious problems. Now, my take on this is that the problems are overdone because all that we're requiring, there's nothing to say, obviously we can't go back in time and change the past. I think that's clear. We can't change the past. But there's nothing to prevent us being part of the past. There's nothing to prevent me going back in time and becoming part of my own history or somebody else's history, so long as the narrative is self-consistent. So let's take a happier version of the mother paradox. Supposing I go back in time and I save a young girl from being shot dead, and then that young girl grows up to become my mother, then that's self-consistent. So this is the other version, so then everything's just fine. It's a self-consistent narrative. And some people say, well, but then what about free will? You can't go back in time and do what you want. You're constrained by the laws of physics to have these self-consistent narratives. But that's always true. I'd love to walk on the ceiling. I can't. The laws of physics won't let me. So we're used to the idea that we can't do everything we might want to do because of the laws of physics. It's another example of that. Nevertheless, some people are still not happy and they want both unrestricted time travel and free will. And there is one other possibility of doing that, and that's that there isn't a single reality, but a vast multiplicity of realities. And that's a very favorite idea at the moment. It's often called the multiverse, sometimes the quantum multiverse. And what it means is that there's a lot of us about, but we're all in separate universes, so we don't see our other selves in these parallel worlds or parallel universes. So a very popular idea. And the point about time travel is if there's a way of slipping between these parallel universes, you could go back in time and you could shoot Mother dead in a parallel universe and return to your own universe, and Mother would be alive and well and with tea ready and all that sort of thing. So maybe if you could have these parallel realities, you could then have this unrestricted time travel with free will. So just to summarize then, before I take some questions, time travel, fact or fiction? Well, travel into the future, definitely fact. We've done it. Not a problem, only a problem of dollars to do it by more dramatic amounts. Traveling back into the past, very problematic. And the dollars here are much bigger because if you want a wormhole or you want to pluck out space-time film or something, you're in for a big budget. But there's just one possibility, and that is this machine here that you may recognize. It's called the Large Hadron Collider. It's in Switzerland. Here it is from the air. It's not really that red tube. It's under the ground. It's a ring-shaped tube, and you probably know that it's designed to make a particle called the Higgs boson. But the point is that it accelerates protons very close to the speed of light and smashes them together at enormous energies. Now, and to give you some idea of the scale of this machine, this is, you see the truck at the bottom right, and this is just one of the detectors that sits on this ring-shaped tube. It's 27 kilometers in circumference. And when the protons collide, they make all sorts of subatomic debris, and the physicists are busy scouring that, looking for the Higgs boson. But there's another possibility. And this possibility is that right up to now I've been talking about Einstein's theory of relativity. And that's our best understanding of gravitation. But there are alternative theories as well, some of them quite popular. Some of them involve, for example, additional dimensions of space. And I'm sure you've heard about that. Now, in those theories, in some of those theories with additional space dimensions, the scale at which you get that foamy stuff I talked about, instead of being 20 powers of 10, smaller than an atomic nucleus, with a corresponding energy 20 powers of 10 bigger than the Large Hadron Collider, instead, the number that comes out where you start getting the wormholes and the black holes and all these funny little things is round about the scale that the Large Hadron Collider is reaching. And that's why some people were scared that when they switched on it might make a black hole that would swallow, first of all, the Geneva, and then Switzerland, and then the Earth, and maybe the whole universe or something. It's all nonsense. Trust me, I'm a physicist. Not a problem. The point being that these, if tiny black holes and tiny wormholes were to form from these collisions, the process that makes them would destroy them very quickly. It's reversible. So if these collisions make tiny black holes or tiny wormholes, they would live only for a very short period of time, but maybe just long enough to see some peculiar time looping effect of the manner that I've been talking about. So this subject of time travel and wormholes, which for a long time just really seemed to be the outer end of the realm of science fiction, has really come back more into vogue when people think, goodness, we might actually be able to see some of these effects in the Large Hadron Collider. Needless to say, nothing has yet been seen. I should say that there is a more serious side to doing this sort of stuff. It is, of course, great fun to think about time travel. But the serious side is that many physicists working on fundamental problems would like to come up with a grand unified theory of the whole universe, a unified theory of all of nature, and for that what you need is a consistent reality. There's no point in writing down equations to describe everything if the equations have internal contradictions. And looping in time looks like it threatens some of those logical foundations. If you can have causal loops, then there are issues. I don't think that those issues are insurmountable, but you can see there are clearly issues. We need to know, not is it a practical proposition, but in principle, is it possible to loop back in time? Because if it is, we have to build that into our attempts to create a grand unified theory of nature. So that is really the motivation for scientists to get involved. But I want to finish, seeing as this is the SETI Institute, by saying that the time travel carries an implication for SETI as well. And that's because something called the Fermi paradox. I'm sure you've heard about this. This is Enrico Fermi, the famous Italian physicist, and he must be famous because he's shown here on a postage stamp, which is cunningly truncated to conceal the mistake on the blackboard, which any physicist here will know that he got his sums wrong. But anyway, he was certainly a genius. And he, in the late 1940s, referred to the fact that the world wasn't teeming with alien beings, as he felt evidence that there were none out there, because they've had plenty of time to come here. And the point is that if you can have time travel as well as space travel, then history and geography really just become part of the same thing. And so the Fermi paradox now gets worse, because it's not a question of why haven't aliens come here from other parts of space, but why haven't they come here from other parts of time as well? And so it opens up that whole issue. It more forcefully concentrates our attention. So there is a SETI dimension, I think, and a Fermi paradox dimension to time travel. So I think on that note, I'll say that this is the end, or perhaps it is, in fact, only just the beginning. Thank you.
Paul, I guess the Fermi paradox also gets extended in the multiverse as well. If it's possible to do time travel backwards, why have we not seen that in our version of the multiverse, and why would our part of the multiverse be different from other?
Right. Once you're into the multiverse, you're into all sorts of problems, because in a multiverse, if it's big enough, anything that can happen will happen. And so then there's a whole set of paradoxes as to why we do or don't see certain things. And the most, we won't get too technical, most famous of these is called the Boltzmann brain problem, that if, at least in some of these multiverses, they will have infinite futures. And then there's always an exponentially small but non-zero probability that in the vacuum, quantum vacuum state of the far, far future, particles will spontaneously appear and assemble themselves into a brain that will have experiences. And because there's an infinite future, there's infinitely more Boltzmann brain experiences than humans on Earth experiences. So why aren't we Boltzmann brains? Why do we find ourselves such atypical observers? All sorts of things like that. But leaving aside the multiverse, which I think opens a whole can of worms, one possible resolution as to why we don't see time travelers from even our own future is that in all of the designs that I've talked about of time machines, you can't use them to go back before the time that you make the machine. So with the wormhole, you put the neutron star at one end, and then You could imagine in the far future that you could go to the supermarket and buy a time machine, and a 100-year time difference machine would cost you more than a 10-year time difference machine. So you move the neutron star in, you leave it there for 100 years, and you put a 30-year time difference in, and you take it away again. So you can now go back 30 years, but you can't go back more than 100 years. So our descendants could not come back now and say Davis got it right. But, of course, if there are alien communities that have been around for a long period of time, they could have made a time machine a long time ago, and they could lend it to us. Or they could come back from their own future, so long as their ancestors made the time machine before now. So one way around it is that you can say, well, that if there are alien communities, that they're not that far along, farther ahead than us, that they made time machines a long time ago. Or the time machines are impossible, or there's a number of other ways of getting around it.
It occurs to me with wormholes, wouldn't wormholes imply a very large mass? I mean, a mass large enough, to have the curvature of space be gentle enough that you could go through it, and have the throat be big enough that you could fit through it without being torn apart. Isn't that like thousands of solar masses?
Right, it's a large something, but it turns out paradoxically that what you actually need to hold the throat of the wormhole open is something like negative mass or negative energy or negative pressure. Because if you think about the whole black hole thing, what you've got is an object that implodes because its gravity is so intense. So you don't want everything to shrink down. You want to hold the throat of the wormhole open. So you actually need something like anti-gravity in the throat of the thing. Gravity around it, but anti-gravity in the middle to stabilize it.
If you're far away from the wormhole, it's still looking like it's a large black hole.
Oh yes. It's going to be a very large mass. So the large positive and negative masses assemble. So yeah, absolutely.
A far away observer sees a large mass.
Yes. So if we were looking for a wormhole in space, we'd be looking for a large mass with certain sorts of light bending and light chromatic effects. Yeah. Yes.
If you remember the famous opera incident where the physicists thought that the neutrinos had gone faster than light, but it turned out it was time dilation. So my question is, how would you cancel the facts of time dilation? So it appeared, so even if it appeared that the time machine is going faster than light, but if there was still time dilation, you would realize that after a while, no, that it wasn't going faster than light.
Right, so the opera experiment that this young gentleman is referring to is an experiment performed at CERN, the same place with the Large Hadron Collider. Very different experiment with neutrinos, which were fired through the Earth to Italy, where they were apparently detected a tiny fraction of a second before they should have been, assuming that they're traveling no faster than light. And so this was much in the media over the past few months, and I even wrote a paper on it myself, which was published just before the retraction, which was very timely, because it now appears that this was well, it's not completely certain, but it looks like it was a problem in calibrating the clocks. So I'm not sure what the question was now.
The question was, how would you cancel the effects of time dilation so it wouldn't just appear as though it was going faster than light, but it actually was?
Right. Well, you see, if an object, there's nothing in the laws of physics to forbid an object going faster than light. That's a curious thing. The theory of relativity says you can't break the light barrier, so you can't start off slower than light and then zoom faster and faster and go through the light barrier and then travel faster than the light. But it doesn't say, there's no reason why you can't have objects that always travel faster than light, and they're called tachyons. We don't know that they exist, but they could exist. And I mentioned the paper I've written. So the paper is based on the fact that if tachyons can exist, they'll have been made in the Big Bang. And so then you have to think what happens as the universe expands, what happens to these tachyons. And so that's a different story. But if tachyons can exist and travel faster than light, you could use them, in principle, to signal, not to travel back in time, but to send signals back in time. So I could send you a tachyon message faster than light, and you could send me back a tachyon message faster than light. And if we're moving in the right way, we can arrange that your answer comes back before I send my question. And so then that gets you into the same type of loop. So yes, it doesn't have to be a wormhole, doesn't have to be a time machine, just has to be a tachyon, and we're already in trouble.
What about the paradox that if you just go back in time, you've just changed time by being there, and you're in a different version of time with a different version of you and future you.
Right.
So then you would instantly just disappear. So you'd need some way to combat that if it's true. Or
Well, I'm not sure about the disappear bit, but at the end I said that if there's not just one world or one reality, there are many of them, and this is a popular idea, there could be many parallel realities, all slightly different, then you could go back and be part of the past of a reality that looks very much like your own world, but you're not actually changing your world. You would change that world. And then if you return to your own world, then everything is normal. But I think that you don't even need to go that far. I think the point is, if you go back into the past, you can become part of the past, but only in a way that is consistent with the future. You can't change something. So you can't go back and kill your mother, for example, before you're born. That can't happen. But you could go back and save your mother, like in the other story. And then everything's fine. Just means that there's certain things you can do and certain things you can't do. Yep.
Years ago, I asked John Wheeler what would happen in a collapsing universe to the second law of thermodynamics.
Mm-hmm.
Would entropy then be decreasing? And what he said was, we haven't been there yet, and we don't know.
Right, I wrote a whole book on this.
I like that. So my question is about things which seem to me to be purely speculative, and in my view are not yet science, because there's not even a conceptual test for them yet.
Right.
Which would include multiverses and string theory, maybe wormholes, and I don't know what the situation is with quantum foam and particles springing out of a vacuum.
Right, all that, yeah, well, each one is different, and each one would take me a whole lecture to get into, but of those things that you've mentioned, I mean, I was careful to say travel into the future is real, travel into the past is very speculative, and black holes are real, wormholes, very speculative. Particles coming out of vacuum, certainly that's no problem, and that's something that is, yeah, oh, absolutely. I've spent most of my career working in that field. Better be real. And then string theory, well, yes, of course, a lot of people complain that's very speculative, and so far there's nothing that, it's not making any tests that distinguish it from any other attempts at unifying nature. So that is a very speculative thing. The multiverse, I think I agree. That's also very speculative. There are I wrote a book called The Goldilocks Enigma, Why is the Universe Just Right for Life? And there I point out there are certain weak statistical tests for a multiverse, but they're not very good. Direct tests seem to be almost impossible. And you're right, so a lot of fun physics and a lot of fun science is off in this sort of never land of crazy stuff, which is fun to think about, but it's not very solidly grounded in experimental physics. So your complaint is perfectly correct. But the trouble is that of course, how is the general public to know? Because all these things get trotted out together. We got tachyons 1 minute and neutrinos the next, and they can't distinguish. When in my books, I always try to make it very clear when something is well established and something is speculation, because often they get conflated.
Is quantum foam and entangled photons?
Oh, entangled photons are fine. Yeah, that's, again, matter of practical engineering. The space-time foam stuff, no, I mean, because we don't actually have a proper theory of a consistent, agreed theory of quantum gravity that could tell us about the structure of it. And the best that we can do, which Planck originally predicted, is the scale at which you would expect something to happen. And Wheeler was a great proponent of what we would now call space-time foam. And also about the recontracting universe. And I did my PhD on that and knew Wheeler very well. And in the end, I think he basically changed his mind. But Stephen Hawking also flirted with the idea of time running backward in a recontracting universe. And then he retracted, calling it his greatest mistake. And so it's an idea that goes around, what goes around comes around, including the cyclic reversing time universe.
A few years back, I was taking a physics course, and they were talking about running an experiment. There was an experiment supposed to be run with quantum entanglement that might show time travel in reverse, using quantum entanglement as the vehicle to prove that. Did you ever hear anything about that?
Well, I'm not sure what experiment that is exactly.
I don't remember the exact experiment. I just know they were going to run it, and I
Are
never
you
heard anything about
referring
it.
to Wheeler's delayed choice experiment?
Yes, I think so. But
that was done. It was in fact performed by Carol Alley at the University of Maryland.
was that about 3 years ago?
No, it was actually many more years than that, but it's been done a few times.
Okay.
The important point, there's a very subtle point about quantum mechanics. The important point here is not that you are able to do an experiment that changes the past. The point is that in quantum physics, because of the uncertainty, we used to think of the future as uncertain. So we prepare a quantum state, say it's an electron moving in a certain way, and we're used to the fact that we can't say definitely where it's going to be at a future time. But the same thing is true in the past. We can't say where it was in the past either. So we like to think there's a definite history, for example, a unique pathway connecting, say, the Big Bang to the present moment. That in other words, there is a single unique history. But in quantum mechanics, that isn't true. So if you apply quantum mechanics to the universe as a whole, there is no unique history. So when we look back in time, when we do measurements that inform us about the past, what we're doing is resolving some of that ambiguity. So there's a difference between resolving an ambiguity and affecting the past. You can't use it to send messages back in time or to change what's in the past. All you're doing is saying the past is fuzzy, and what we do now affects the nature of reality that was in the past. Now, it's a subtle point, but I've written at great length about it in the book called The Goldilocks Enigma, I already mentioned, towards the end, all about Wheeler's delayed choice experiment, what it really means, and how this changes our notion of the nature of the past, but it doesn't provide a way of changing the past. So it's in that book. Very subtle, I'm afraid. Yeah.
Well, at the risk of showing my lack of knowledge,
It's all right.
I'll throw out this question.
There's a lot of things I don't know.
Well, does it make any difference in having this time effect, slowing down of time, whether you are accelerating towards the speed of light or close to it, or whether you're going, say you got to the speed of light and then you just keep going at a constant velocity near the speed of light?
Right. It's actually elementary mathematics to work it out.
To me.
No. I'm talking about junior high school level mathematics. It really is very, very simple, and the formula is very simple, and it doesn't require anything except elementary algebra. Well, for that one, you actually have to be able to perform a simple integral, but that's all you need to do. And then you can work out precisely what the time warping effect is along that trajectory. And basically the story is that if you continue to accelerate, of course you're getting closer and closer to the speed of light, and that makes the time warping effects even greater. So if you accelerate at 1g, for example, for a year, Fred Hoyle once told me the answer. I can't remember what it was, but the effect is enormous. You're traveling so close to the speed of light. The time warping effect is really enormous. But another statistic to remember, which I found very arresting, is cosmic rays are particles moving very close to the speed of light. And if you take the highest energy cosmic rays and imagine you were traveling with one of those particles across the galaxy, it would take only 15 minutes in your frame of reference to cross the galaxy, which is quite something, isn't it? They're moving so fast.
I was looking at some Feynman diagrams, and the implication of quantum tunneling. An electron implies that the electron's going backward in time. Is that true for quantum tunneling?
I think you mixed up a couple of things there. So Feynman had the idea that a positron might be an electron going backwards in time. It's not quite the same thing as quantum tunneling, but seeing as you raised quantum tunneling, because that's another research interest of mine, I've written some papers on that, there's the old question about how long does it take a particle to tunnel. So for people who don't know about quantum tunneling, so I presume behind there's a window. Okay, so now if I got a rock and I threw it at the window, it might very well smash the window and go through, or it might, if it's a tough window, it might bounce off. What we wouldn't expect is to find the rock on the other side of the window without the window being broken, but that's exactly what happens with quantum tunneling. You find an electron at a barrier and it appears on the other side. without having shattered the barrier or apparently surmounted the barrier. So, and there's a real effect, of course, very well known. And then the question is, when it disappears from one side and appears on the other side, how long does that take? And that's a very difficult problem. Not difficult in the sense of the mathematics is hard. It's just difficult to decide what are your criteria for measuring the time interval. And I've got my own take on that. It would get too technical to talk about it. But there's nothing going backward in time. But there was an experiment that was done a few years ago which gave that impression perhaps, which was sending, in this case it wasn't an electron that was tunneling, it was a photon. A photon can also tunnel through barriers, and so it was an experiment where, a quantum interference experiment, where one path went like this and another path went through a barrier like that, and then you could take the barrier away and put it there, and you would expect putting the barrier there would slow down the photon taking that path. Did the opposite, sped it up, and you thought, well, if it's traveling at the speed of light and it's now getting there faster, doesn't that mean it's going faster than light? The answer is no, but for all sorts of subtle reasons concerning the shape of the wave pulse and other things. But there are these effects in quantum mechanics that look like they're coming very close to, in some way, breaching the light barrier. But when you look at the fine print, you find they never actually do it.
Okay, probably I'd encourage you all to come and chat to Paul for briefly anyway.
Yes,
He's got to
10
catch
minutes.
a flight back to Arizona, and to make sure you can take this time machine along and make sure you don't miss your flight or something like that. I'm sure
Thank
it's
you.
hidden in
Yeah,
there. The instructions are there. Thank you, Paul.